All right, hello everyone. Welcome to the reading group this week. So this week's reading group, I wanted to talk about architecture description in VTR specifically. So architecture description is a very interesting topic because it's kind of the bread and butter of what makes VTR VTR. VTR is not just some CAD flow like Quartus or Vivado. VTR is designed to work for any FPGA, not just one particular family or one particular type. And as such, it needs to have some way of the user describing to the tool, what does that FPGA look like? What are the tiles? How do they interconnect together? And what is within each tile needs to be put in here. So whether you are an FPGA architect, a researcher, or a student who wants to learn more about FPGA architecture design, the knowing more about the architecture description file will be very valuable to you. So that's why I wanted to make this discussion today. So let me just hop right into it. So FPGA architecture are very interesting, and I wanted to try and break it down into two distinct groups, which I call global and local. This isn't the most proper terminology. Global means a lot of different things in FPGA research and CAD, but I'm going to use the word global, but take it with a grain of salt. It's not the proper terminology. When I say global, I really mean inter-tile. So when I'm talking about architecture description, we want to figure out where am I going to put all of those blocks onto the FPGA and how do they connect together? Because we're not going to, most FPGAs these days are island style, where we have islands of logic connected by interconnect. And at a high level, all I really want to say is I have, let's see, 16 logic blocks in the middle, surrounded by IOs, and I have a bunch of switch blocks and connection blocks in between them. That's the global view, but in order to do a proper packing, I actually need a bit more information. So VTR actually requires not just the global view of the FPGA, but we also need to provide a local view. I want to make sure this doesn't get blocked. Hang on. There's a lot of fun that goes into making these. Cool. So when you define the local interconnect or the intra-tile complex blocks, what you really are telling VTR is what is inside one of these tiles. And this is quite useful because this means that if I could represent my FPGA to VTR, I can describe any real architecture as long as I can tell VTR it is island style and it looks like this. And inside each of those tiles are this piece of information. And I will talk a lot more about what these pictures mean. But really, I want to first talk about the goals. So what are the goals of architecture description in VTR? I basically stole this from Jason Liu's paper on this topic, so you can read that paper. I have that as a citation at the end. The very first goal is that it must be expressive. I want to express many different FPGA devices for CAD research. If it was too focused on one particular class of FPGA, that wouldn't be very good for CAD research. We want to try different architectures and see different architectures. And it should contain enough information to create a valid placement and routing solution. What that means is that there's a lot of detail that's in the weeds from when it comes to an FPGA architecture. Do I really need to know that this is made up of 4 transistors and this one's made up of 2 transistors and they have these different connections? Really, all I need are just the bare minimum of what do the CAD tools need to understand this stuff. It should also be able to model modern, complex FPGA architectures. Thank you so much. They should be able to model modern, complex FPGA architectures because, I mean, we're using this as a research tool. But also on top of that, VTR is actually used by many real FPGA vendors who are using VTR as part of their CAD flow. For example, QuickLogic, Zero ASIC, and a few others who remain unnamed. People actually do use VPR as part of their actual CAD flow, so it's actually important that we're able to represent their architectures as well. Finally, or next, it should also be simple. We want it to match closely with an FPGA architect's existing knowledge and intuition. What does that mean? It shouldn't be focused in on what the CAD tools want. It should be an FPGA architect, someone who laid out the transistors and everything of the FPGA. When they write this architecture description file, it should be relatively easy for them. It shouldn't be like, oh, I need to change my thinking process into this like programming view. It should really be a description of the architecture. So the description should match the physical implementation as much as reasonable. Notice how I say as much as reasonable. There are times we're going to have to break this. I'm not going to talk about this in this talk because it's super complicated, but there's a discussion of whether what's physical and what's logical in the FPGA architecture and the FPGA architecture. And for the most part, I'm going to be avoiding that in this talk, but this is kind of what I'm talking about. Anything that's matching the physical description as much as possible, we call that physical. And any time that we kind of bend the truth a little bit, we usually call that logical. And then finally, it should be concise. It should not be too detailed to become challenging to use. It should be very easy to use and be all-encompassing. So many of the physical details that are not necessary for CAD should be omitted. If we don't need it, we shouldn't have it. So, is this clear so far? The goals of what we're trying to do here, why the architecture description file exists? Sweet. So, the architecture description syntax. This is what we're waiting for. What do we use? Do we use a text file? What do we use? Well, it's XML based. If you've worked with HTML in the past, it's very similar. What you have are tags, and the tags can contain other tags. That's all it really is, and they're usually described using the caret symbol. I'll show some examples of this and it'll make a lot more sense. The XML tags describe some aspect of the FPGA, and the subtags provide more details. So for example, we have a tag called tile, and inside that tag, you'll have another tag that tells me what is inside that tile, and so on and so forth. So this just provides more and more details. The highest level tag in the architecture file, and this is what tells VTR this is a valid architecture file, is if your top level tag is something called architecture. This is just our way of checking to make sure, yeah, this is an actual XML file for us. Someone isn't just passing in some random XML file. And this is what contains the entire architecture. The top level tags, which is kind of confusing, architecture is the top level, but ignoring that tag, the top level tags within the architecture tag provide information on the FPGA architecture. And the subtags, again, provide more details on each of those top level tags. This will make a lot more sense once I get into some examples. VPR will interpret this description to perform placement and routing. And as a quick example, you can actually go into this architecture, which I'm actually going to go through at the end of this talk. And if you want more information, the full design document for the architecture file is right here. Yes, Amir.
Another reason the architecture tag exists is that XML files must have one single top-level root tag.
I actually didn't know that, actually. So what Amir just said is the reason why we have an architecture tag like this is that XML must have one and only one top-level tag to be proper. So we need, for example, we can't have multiple tags at the top level. We need to have one and only one tag. Thanks, Amir. That actually makes a lot of sense. So yeah, I can be wrong. So always double check my work. So my goal, I want to describe that. This global FPGA description. What does that look like? Well, the very first thing is that we only model island-style architectures. So if you're taking Vaughn's FPGA architecture course, we're going to talk about this maybe in like 2 or 3 weeks. This describes a set of FPGAs where we have islands of logic. No, there's some noise going on out there. We have islands of logic and connecting them together. And the idea here is that there's a lot of symmetry. Because of all this symmetry, it makes it very easy to lay this out, and it makes it very easy to turn this into a chip, or relatively easy. It also makes the CAD problem a lot easier because we have spatial symmetry. If I wanted to move a block from here to here, it's not that hard to do because there's parallelism between this one and this one. There's duplicated information. So I can reasonably swap these two without an issue. So to describe the global FPGA, we need to describe the following. We need to describe all the tiles that exist at the I/O level. So there's an I/O tile. There's a logic block tile. The logic block tile has this many inputs, and they're on this side of the tile. It has this many outputs. It's on that side of the tile. At a physical level, what are the tiles and how are they oriented? Next is the layout, or what we call the layout, which is where the tiles exist on the device, and also how big the device is. So is it a square device, so n by n? Is it maybe n by m? Is it 20 by 30? Or is it, where are the IOs relative to the logic blocks? That's what the layout is. There's also this idea called auto. This is specific to VTR, and I bring this up just because it's a little confusing. In VTR, we actually can allow the user to not specify the size of the FPGA. So for example, we'll just say the device will look like this. It's going to have a perimeter of IOs and the inside's all logic blocks. Now this one happens to be 6 by 6 in this picture right here. But if I made it 7 by 7, you could easily extrapolate what that would look like. If it was 8 by 8, 10 by 10, VTR plays that trick to allow you to describe any architecture you want much easier. So VTR can change the size pragmatically instead of having to have the user define different sized architectures for every single possible circuit that could exist. So that's where the auto layout comes in. It's just kind of interesting. And next up, we have the global routing information. That is the switch blocks, which are going to be handling the connection between the channels. So these orange wires that span the entire chip, these are called channels. And the switch blocks are what switches between the channels of, like, for example, the X channels and the Y channels. I showed them here in orange. The connection blocks are these ones shown in yellow. They connect the logic blocks or the tiles to the channels. Notice that we separate the connections going from the tiles to the routing channels and the channels to channels. We separate that out just kind of logically, but in reality, you might actually expect the layout to actually merge these two things together. This is more of just a logical understanding of this problem. And then finally, there are also direct connections. These are kind of a necessity. Let's say this logic block has an adder inside of it with a dedicated carry chain, and that carry chain must go down to the logic block below it. We would see a direct wire going from one tile to the other. These are called direct connections, and I didn't show any in this figure because I didn't want to overcomplicate it. And we want to keep this as general as possible to describe many FPGA devices from the same family. So for example, if I have a device family like this one, which has a bunch of IOs on the perimeter and logic blocks, I could describe a whole family of devices as long as they all have these tiles and their connections and switch blocks are somewhat like this. And then I can play with this. I can put the IOs only on one side. I can put the IOs in the middle. I could remove most of the IOs and leave only one in the top left corner. Whatever my device actually is, or my family of devices will be, I can describe them in a high level. So that's the global level. All good? Cool. The local complex block description is now we're going to go inside each of those tiles to describe what's inside of them. So in this case, what I have is my logic block. Let's say it has 4 basic logic elements inside of it, where the inputs are a full crossbar, and each output can feed back into that crossbar and or go out of the chip. And inside of a single basic logic element is a LUT, whatever size it is, feeding into a flip-flop with a multiplexer for interconnect. This is just an example, but it could really be, let's imagine if it was 8 BLEs, or maybe it has a special adder chain inside of there. But the idea here is we want to keep it as general as possible. So how we chose to do this in VTR is through a hierarchy description. Notice that this BLE complex block is within the LB complex block, and then the LB complex block is within the tile. This is pretty common. You'll have complex blocks that contain other complex blocks, which contain other complex blocks. That's how we chose to model this, is a hierarchical description. Now, a brief aside. I want to just mention this in the recording, but I'm not going to put it in the slides. This is where we're starting to hit some logical stuff, not physical. Because in actual hardware, when we actually put the transistors, this hierarchy doesn't exist. There's no such thing as a hierarchy of primitive blocks. In reality, it's Verilog modules, really. And these become transistors on a flat FPGA. But it's convenient for us to model this as a hierarchy. So that's why we model it as such, and therefore it is a very logical understanding. This will make more sense when I talk about modes, but we're not going to go too in depth on that. So to describe the local complex blocks, we use the tag PB type. To be honest, I don't know what PB stands for. I couldn't find it in the documentation. I believe it stands for physical block, which is really confusing because I just told you it's logical. Maybe it stands for primitive block, but these aren't primitives. So Amir, do you know what PB stands for? Yeah, I think it's physical block. But as I said, we try to avoid that terminology. We really call these complex blocks. So I'm going to use that terminology. So the top level complex block, this is the top of the hierarchy. We say this tile implements this complex block, or it's a little bit more complicated than that. I'll get to an example of it. It is the highest level of the hierarchy, and its role is to connect the inter-tile routing to the intra-tile routing. It's basically how we get the inputs to the complex block into the tile. This is also called a cluster in our CAD terminology. It's a little weird, but in reality, when we do packing, we create a cluster that reaches to the top level complex block. That's our ultimate goal. And then once we do packing, we can start doing placement and routing. Or if you do this completely flat, good luck, but you could also do that. You know what? Maybe it does stand for primary block. That does make sense. Okay, I have a chat message. I'll read that afterwards, once I get to a good stopping point, but thank you, Peter. So the top level complex block was that. Let me keep going. The intermediate subblocks are the next level in the hierarchy. Remember how I said PB types can implement other PB types? Complex block contains other complex blocks. The ones in between in that hierarchy, we call them intermediate. Again, they're really just logical. We're just trying to create connections between all these blocks. But once we get to the bottom is when we finally get to something really physical, which we call the primitives. They are still kind of logical, which is why it's so complicated to talk about this type of stuff. But the primitive is just the leaf complex block in the hierarchy. So you see these red blocks down here, which is a LUT and a flip-flop? These are complex blocks. They are defined by a PB type. However, because they don't contain other complex blocks, we call these primitives. And when you write your Verilog and whatever, and you compile this down to a netlist of LUTs and flip-flops, those LUTs and flip-flops are going to be implemented onto those primitives eventually. So let me take a step back. We have our FPGA grid of tiles, and those tiles contain primitives at the base level of their hierarchy. And so when I take my circuit and I'm trying to map it onto that FPGA, all I'm really doing is saying I have this LUT that the user wants to implement in their circuit, and I'm going to place it somewhere on that FPGA grid within that tile inside of a complex block. That's what packing, placement, and routing are really doing. Well, packing and placement, routing does something else. I just wanted to make this very clear, and this is why I make this distinction between global and local here, even though they're terrible names. So complex blocks and subblocks, so the complex blocks are which are contained, they also might contain modes. I'm purposefully avoiding this in this presentation because I want to keep this kind of introductory. But let's imagine that I have some kind of mutually exclusive logic that may be implemented. For example, let's say this LUT right here is actually a 6 LUT, or it could be two 5 LUTs, but it can't be both at the same time. So we use what are called modes to kind of differentiate that. So a PB type could contain modes which tell you that you could be one of the or the other. That's all it really is. And how you would look at this is you'd see a box here that would have that mode, and you can say it's either going to be a 6 LUT or it's two 5 LUTs with the connections all set up. I'm not going to cover that anymore because modes are really complicated. If I end up making another one of these videos, I will go into the more detailed aspects like modes. Are there any questions though on the local complex block descriptions? Let me go see what the comment was in the chat. So, uh, So what Peter is saying is once upon a time, it may have been placed block or placeable block. That actually makes sense. That's what Peter thinks PB stood for. It predates quite a bit of physical and logical delineation that became more important with the advent of the tile tag hierarchy. So I think Peter's absolutely right. It could be placeable block, which is really confusing because the innermost ones aren't technically, or the intermediate ones are certainly not placeable. The lower ones are technically placeable, the primitives, but we don't do that in VTR. And then the outermost ones, those are actually placeable. Thank you, Peter. That might actually be what it is. Okay. Oh, let me just, The definitive answer would come from Vaughn or Ian Kuon, who are not here right now. Vaughn is working on his own presentation for his course.
Base primitives and VTR, those like be something that you worked on.
You can't, even I can't do that actually.
AP does that.
AP actually doesn't place the primitive blocks. The one that I implemented doesn't place the primitives directly. You can't right now in how VTR is implemented. It's not like we can't do it because it's physically impossible. The data structures are set up in VTR that makes it very impractical right now. We need to make some major changes. Haidar, you want to do them? No. So Amir was just talking about can we do a primitive level placement in VPR? As of right now, not really. So syntax. This is our entire architecture description file. Now, I am heavily using these dot dot dots to get away with a lot of cheating here, but this is literally what an architecture description file will look like. This is the bare minimum of what you need. Boop. These two are what describes the FPGA layout. So it says these are the tiles and the primitives that they implement, and the complex blocks that implement them. And here is the layout, how they lay out on the FPGA. Next, these orange ones are the global inter-tile routing description. They describe the delays and all of the other interesting stuff about the actual global routing or inter-tile routing. These are things like, what is the switch block? How is it implemented? What's the channel width look like? How is it distributed? And so on. That's described by these orange ones. And then finally, these green ones just describe the local complex block descriptions. As I said, these are the bare minimum that you need to define an architecture in VTR. This dot 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 at the bottom is actually hiding something. There are more complex architectures that you can describe in VPR, but I'm trying to keep it simple here. We're not going into the third dimension. We're not talking about Knox here. Just very basic 2D FPGAs for today. So I'm going to look at those blue ones. Yeah, we're going to look at the blue ones first. See that FPGA up there? I want to implement that in VPR. What's the architecture description file going to look like for this? Well, the very first thing is I'm going to use the tiles tag. The tiles tag is at the top level is just going to say, I'm going to describe to you all the tiles that exist in the FPGA. There is one named IO. And again, I'm making heavy uses of the dot 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 here. I will show a full demo with exactly what goes inside of here. But this is what's going to go inside that dot 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 is what are the inputs and outputs? Where are they located on the tile? And which complex block does this implements this tile or is implemented by this tile? There is a concept of subtiles and other things like that, which I'm not going to cover, but it makes it a little bit more complicated. So there's another tile. Its name is LB. And again, in those dot dot dots, it's just a description of what that tile is and where the inputs and outputs and the complex block that implements it. That's it. Those are all the tiles in this particular architecture. You've had other architectures, you'd have more of these. Next, I need the layout tag. I've told VPR that a tile named IO could exist, and a tile named LB could exist. And now I need to decide where on the chip will that show up. So for this example, I'm going to use a fixed layout, not an auto layout. I'm going to name it example because in VPR, you can actually have many fixed layouts. Oh, so in VPR, you can actually have many fixed layouts. And when you're routing, you can actually.
Run.
Oh, okay, gotcha. It's a small world, I guess. Anyways, so in VPR, you can have many fixed layouts. And so you could actually have many of these fixed layout tags. And then in VTR, you can say, I want to use the example fixed layout. I want to use another fixed layout. This allows you to have many devices on in your architecture description file. So, and for my fixed layout, I fixed it by saying it has a fixed width of 6 and a fixed height of 6. So that's this one right here. Now you might sit here and go, isn't this 4 by 4? Because I see 1, 2, 3, 4, and then 1, 2, 3, 4. But you also have to remember that there are these IO blocks on the perimeter here. Even though these corners are empty, we still consider those as a tile. We just call it the empty tile type, so it doesn't really do anything. So in reality, it's 1, 2, 3, 4, 5, 6 times 1, 2, 3, 4, 5, 6. So that's why this is 6 by 6. Now we're going to describe what the layout looks like. Now in VPR, we use a description a lot like you're a painter. We're going to paint in the layout of the FPGA. So we're going to start by painting our perimeter. I'm going to paint a perimeter of I/O around my FPGA. In this case, because it's 6 by 6, it means the first row and last row, the 0 and 5th, are going to be IOs, and the first and the last are going to be IOs. Next, I'm going to say that let's erase those corners. I don't want the corners because in the real world, we're probably not going to be able to get the IOs from here over to this logic block, so we usually omit the corners. A lot of real world FPGAs kind of do that. And we're going to make those empties. So remove the IO. And then finally, I got to say what's inside the middle, which we then fill with logic blocks. So what we do is we say, everywhere else that I haven't specified yet, make it an LB. Now you may say, is this read like top to bottom? That's what this priority is saying. The higher the priority, the more that will be set. So for example, this bottom left corner is on the perimeter. It has a priority of 100. But then I said that the corners are empty and has a priority of 101. Because the corner has a higher priority, we remove the corner. If I made this 99, for example, then we would have IOs in the corner. And that's not what I want. I want to remove those IOs. And then finally, this fill says, with a low priority, fill everything else. I don't care what it is. These numbers are pretty arbitrary. It's just that this number needs to be the smallest, this number needs to be big, and this number needs to be the biggest. And that's it. I've defined my fixed layout. Again, I can describe more fixed layouts, but I decided just to make one for this example, and I'm done. So that's how I describe the layout of an FPGA in VTR. Pretty easy, right? I'll show you guys an example. It's not that easy, but once you have an example, it's easy to modify it to make it whatever FPGA you want. Is this clear to people? Great, because it's only going to get harder from here. So the top is a description of the tiles that may appear on the device, and the bottom is a description of how the tiles are laid out on the device. I just like add little notes here so that if people watch the slides later, they have the notes. So now we're going to talk about the Intra-Tile routing description. We're going to have some fun here because VTR is designed to change the size of the FPGA for architecture research, research. We're trying to find different sizes of FPGAs. We want to change the channel width. How many wires are in each of these channels? VTR wants to sweep those to try different ones for research purposes. So our description needs to be general enough so that to allow that kind of research. So we're going to start with the device tag, which I think is a terrible name. The device tag describes some general aspects of the device that won't be changing. So we have our channel width distribution. This is going to tell us that for each of these channels in the X and Y dimension, how are they distributed? Now, for most people, for when they're doing their FPGA architecture descriptions, they're probably going to use a uniform distribution. That means the channel width in the X dimension is always the same vertically up and down, and the Y we're going to do the same. But you can imagine that maybe I might have more channels in the X dimension for whatever reason, or more channels in the Y dimension because you need more routing for whatever these blocks might be. Some of these blocks might have all their outputs on one side, for example. So you might want to add more channels to that. Or maybe the chip is not uniform across. So for example, you might want to add more channels on the right side than the left side for whatever reason. Maybe your IOs are all on one side. This just gives you a general way of describing your architecture. And so that's just a quick little thing. And then also inside the device, we describe what is our switch blocks. So when I have all my channels and I have connections between those channels, how should they be connected? Should they be fully connected? Meaning that every single wire has a dedicated wire to every other wire. Don't do that. In FPGA architecture, we don't do that because it's very inefficient for lots of reasons. But a very common type of switch block is called the Wilton architecture. I implore you to go look at other readings. I'm not going to try and describe it here, but basically it's just a way of connecting a wire in one channel to the other channels without being fully connected, but in an intelligent way. If you're working in Jason Anderson's CAD course, I think he just talked about this. Am I right?
Yes.
Yes. I remember that lecture. It was very good. And then this FS will make a lot more sense in that case. I'm making heavy uses of dots again. There's a lot more in here. I'm avoiding that because it's kind of a pain, and I'm just trying to show you with a bare minimum of what you need. That's it for the device. Then we have the switch list. This isn't what you think it is. So you may look at this and say, hey, Alex, didn't you just describe the switch block right here? What's this switch list doing? I'll show you a demo of this. This is just describing the delays within the switch block. So it's just some extra information that's necessary for for the switch blocks that you will implement. Segments are something similar. Again, I have to reserve this to another talk because how segments work are actually kind of complicated. If you look at the FPGA that I drew up here, we see that this orange segment is of length 1. The connection block kind of sits on top of it. It has length of 1 because it goes from one channel to another. In real FPGAs, we often don't do that. We will actually have the channel be quite long. So this orange wire will actually span maybe 4 blocks. And then it will just connect at different points along that area. It's a little bit of an interesting detail. As you go down FPGA architecture research, you'll understand why we do this. It's for routability reasons, but it's described in the segment list. And I'll show an example of this again in a demo. Finally, the direct list, as I said, there might be direct connections between logic blocks. That's described here, or at least at a high level, we say that they will exist here. But I'm saving that from here. So the top part is a description of the general information of the device. And these bottom 3 are a description of the metal and connectivity characteristics of the intertile routing wires. I'm just trying to be complete here. In reality, the more important stuff is that we have channels, we have switch blocks, and we're trying to define how they connect together. So how are we doing? Cool. This is the last part, the local complex block description. And this is the most complicated part by far because Jason Liu wrote a whole paper about this when he introduced this. The paper is actually very good at describing this, and it's extremely important for people to understand this if you're working with packing or if you're trying to describe your FPGA architecture for its like modes and all the different operations it could be doing. This is that hierarchy thing that I was talking about before. So we have the example on the right where I have my logic block, complex block, and a BLE complex block in the top bottom right, which I need to make sure I can show. So how are we going to describe this? Well, we'll talk about this. I actually don't even think I want to talk about this, what models does, so I'm going to skip it for now. I'll talk about that in a moment. But then we're going to describe all of our complex blocks. So what I'm going to do is create a top-level complex block named LB. Cool? And my tile, capital LB, is going to say, I implement this PB type in those ... dots that I hit. And inside this top level one, which is basically this blue box, I now need to say what's inside of it. Well, it has an input. That's the input right here. I'm going to name it I, why not? And let's say it has 16 pins, 16 bits, for example, in this orange connection right here. It has an output. Its name is O, and it has 10 bits of output. And it also has a clock. We need to describe all the inputs and outputs for this complex block because we need to describe not only what's inside the complex block, but what the routing looks like inside of there. So I need those pins. And next, we now start creating that hierarchy. I now create a middle level complex block, which I'm going to name capital BLE. And notice that I say that there are 4 of them. 1, 2, 3, 4. So what I'm saying here is that my PB type LB has these inputs and outputs and has 4 BLEs inside of it. Now, because this is a hierarchy, I'm going to describe what the PB types are like for the BLE. Well, again, we have our inputs and outputs. I'm not going to repeat that, but it's pretty easy to extrapolate what this is supposed to be. I have my input, my output, and my clocks. And then I have my PB types for both the LUT and the flip-flop. Now, these are very special. I give these a BLIF model. This is what this model section is all about. When the user provides you a netlist, that netlist is going to connect a bunch of things together, like LUTs connect to flip-flops in the netlist. Or maybe there are special blocks, for example, multipliers and adders, that you've told your synthesis tool, hey, you can generate multipliers and adders if you'd like, put them in the BLIF file, and I will put them onto the FPGA. This model section is where you describe all the different models that can exist. like LUTs, flip-flops, and other things like that. Now, what makes VPR a little confusing is that there are models that we infer. So for example, dot names and dot latch, these are so common. All FPGA architectures will have a LUT. All FPGA architectures will have a flip-flop. So we don't require you to put that in the model section. But let's say I had a primitive that wasn't a LUT or a flip-flop or an IO, then you'd have to put a description of it up here in the model section. I'm avoiding that in this presentation, but trying to keep things simple. So great. Am I done? I have my LUT primitive, and I have my flip-flop primitive, and I define the inputs and outputs. That's not enough information. I'm missing something. Look over here in this picture. I have to somehow tell VPR that the output of this LUT goes to the input of the flip-flop. We do that through an interconnect. We say that the output of the LUT, and I put dot 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 here just because I'm out of space, but if you actually look at the how the syntax for this, it's actually pretty straightforward. It basically says connect the output of this LUT to this flip-flop. Connect the output of this LUT and the output of the flip-flop through a mux to the output. Connect the clock to the clock pin of the flip-flop. That's all the interconnect tag actually does. It kind of dictates how the interconnect actually works. And I'll show a demo of this. So cool. I've now defined what a BLE is, and I've said there's 4 of them. Am I done? Whenever I ask that, it's probably no. Because I've defined my top level logic block, this blue one. I've defined the inputs and outputs and the clock, but I've also defined all the primitives inside of it, or all of the complex blocks inside of it. I haven't defined the interconnect. It's an interconnect block. This is this hierarchy coming to play here. And this one's a little bit more complicated because I have a full crossbar here. But basically all it says is just create a full crossbar from the inputs and the output of the BLEs together. Again, I'll show a demo on this. We end the PB type. And there's also the PB type for the IO, which I'm not describing here, but it's pretty straightforward. And it actually does use a mode. So I will show that quickly later. And finally, I finish. As you can see, this is a hierarchical approach where I have defined the PB type for the logic block by describing the complex blocks within it, by describing the primitive blocks inside of them. And this will tell VPR what this looks like. And it will also tell VPR what does the interconnect look like. So when a VPR actually has to route this thing, it's possible. Is this clear? Any questions on this? Yeah.
We just described the interconnect.
That's correct. Anything I put in yellow or orange, I did that on purpose. Those are the interconnect. Yeah, it's a little confusing because wouldn't the crossbar be almost like a primitive? We do make a distinction here when interconnect is defined as more just like the programmable routing of the FPGA. And the red primitives on the bottom right, those are the netlist primitives that you'd have when the user defines their netlist connectivity, the netlist functionality. That make sense? No worries. Cool. This is my last slide, I think. Yeah, I have some resources. But I wanted to walk through, because I have another 10 minutes, I want to walk through a full demo of what a real architecture file looks like to show you guys that I'm not lying. So this is called K6N10 40 nanometers. We try to make our naming as clear as possible. K6 means that it is a 6-input LUT architecture. N10 means each CLB contains 10 BLEs. I showed 4 in my example. This one has 10. So you can find some more information on this. You can actually read through this if you'd like and see all the authors. But as you can see, the top level tag is something called architecture. We then have this model section. This comment's actually a bit old, so I wouldn't trust it. But in this case, this architecture does not define any new models. It's using LUTs, flip-flops, and IOs, whatever we define in VPR as being normal. We now have the tiles section. So for this architecture, we have 1 tile? No, there's another tile down here. So it has 2 tiles. It has the IO tile, so this is where I was putting those dot dot dots for a reason. In VTR, tiles must contain subtiles. And in this case, the subtile has a capacity of 8. What does that mean? If I go to my architecture file, which I'm going to go to right now, and I look at this picture, where am I? There we go. And I look at this picture of the FPGA, I drew this as one box. But in reality, there may not be just one IO there. We might have 8 of them stacked on top of each other or within the same region. And so in this case, what we're saying here is that there are 8 IOs in that one tile location. That's all that really means. And don't worry about equivalent sites here. That's a very advanced feature, but we need to define it. And in this site, we have a PB type called IO. This is where I link the tile to the PB type that implements it. And we also need to describe the input, the outputs, and also the pin locations. This is again is another place where we actually connect the PB type to the tile. And we do that by saying, hey, look, on the left side is our out pads and in pads. On the top side, we have out pads and in pads. We basically have our outputs and inputs on all sides. Zoom in a little bit? Absolutely. Perfect. I'm happy to zoom in. Next up, we have the CLB, a much more interesting one. And if I'm just glossing over things. You can look at the architecture description syntax for all the little details. I'm skipping over some things that I don't think are very important for this discussion. So this subtile is named CLB, but notice it doesn't have a capacity, which means its implied capacity is 1. So in this case, this tile is nice and easy. It just has one thing inside of it, which is great. And in this site, we have the PB type CLB. They happen to name the tile, subtile, and site, the PB type, the same thing. They just did that. Don't worry about it. Thanks, Robert. And again, we're going to say what are the inputs and outputs of this tile. And I should really draw to your attention this. Anyone know what this is? Inside of my tile, I have this tag called FC. What could that mean? I'm looking at a mirror because I'm hoping you know it. No? Then I'm glad I brought this up. I was planning on skipping this because I thought it might be obvious, but apparently it isn't. Okay. So if I look back at my figure here, remember these orange, the yellow connection blocks that connect the logical block to the channel? I didn't define that in my device section. I only defined the switch blocks. So who defines how many connections go from the logic block to the channel? Because it would be crazy if I connected every single output to every single channel. The channel width could be 100, and that's a lot of connections. So I want to keep that limited. What that FC tag was doing is it's telling VPR how many times, or what's the percentage of connections from the output of my tile to the channel. So if I go back to my example, it says that this is a fractional one, or fracturable. I gotta double check what that means. But what it's saying is that whenever we have an input coming into the tile, 15% of those input pins are actually connected, or 15% of the channels are connected to the input pins. And then 50% of the outputs are connected. This is just defining what the connection blocks, or the connectivity of the connection blocks. We do this within the tiles because different tiles will probably have different connection blocks. Sorry for that. It's kind of annoying this is located here. I think Peter has a question. Frac means that FC is specified as fraction of the channels. You can also specify an absolute number of connections. Peter's awesome. Thanks, Peter. I really appreciate it. So yeah, fractional. Okay, I have now defined my tiles. You can see why I didn't put this in the slides. Now we're going to go inside the layout. You're going to say, Alex, that does not look like what you showed me. And because this architecture is used all over the place in VTR, we want it to be general. We don't want to say that you have to be 6x6 or 8x8. We want to let VPR automatically select whatever size it wants. So that's why we're using the auto layout. And it has an aspect ratio of 1.0. That means the width and the height are scaled. It's going to be n by n, basically. But this will look familiar. Perimeter of IO, the corners are empty and filled with CLB. I wonder where I got my example from. So that's how we define the layout. And all this means is that VPR will select the new size and it'll just change that size however it sees fit. Inside the device is where we're going to start seeing some area and timing parameters. I skipped these from my slides, but you can look into these. This is basically how we tell VPR how big things are, which are useful for CAD algorithms. And there's our channel width distribution. There is our switch block. Again, it's a Wilton. And then this connection block here isn't actually the connection block that's going to be used. All we're really doing is defining the timing. So that's what this thing over here is trying to say. It only affects the timing in the area, but the connectivity was defined within the tile. To be honest, I wish it was defined here because that would make it nice and clean. But as I said, different tile types will probably have different connection blocks. So that's why this one just defines the timing characteristics. And this switch list right here, as I said before, is just defining the timing characteristics of those switch types. And these are the segments. Segments are way too complicated for this type of talk, so don't worry about it. But you can find a tutorial in VTR which describes exactly what this is. And if you're in Vaughn's FPGA architecture course, I believe you actually have to mess with this in the last assignment. So you'll learn a lot about this one. Those are our segments, and now we're in the complex blocks. Could you believe that was the easy part? So now we're in the complex blocks. But this is actually really close to what I showed in my slides. We're going to have a PB type named IO. It has the following inputs and outputs and the clock. And now we get to see the first use of the modes. What we're saying here is that this IO complex block will either be an input or an output, but it can't be both. That's all we're saying right here. And if it is an input, it will have a primitive called input, which is great. And this is the interconnect, basically saying connect the input to the, let me just make sure this is correct. InPad, yes. Connect the input to the InPad. And then we have some delay information, which again, I am avoiding for this type of talk. If you're an output though, you're going to use the output primitive. Notice what's going on here. For this complex block, you are either going to be an input. Let me just double check something quickly. Yep. You're either going to be an input primitive or an output primitive, but you can't be both. Again, this is why I'm saying this is logical. When we actually look at the physical implementation, that's not what's happening. There has to be an input and an output both there, but I'm going to be selecting between them. So we create this logical model to make it easier to understand for ourselves. And then power, I guess we're ignoring power for now. So, and then the CLB, I've already kind of talked about this, so I'm just going to breeze through it. We have our inputs and outputs. We have our FLEs, but now there's the mode that I was talking about. Your FLE will either be a 6-LUT mode, or you're going to be in, these get long. Oh, we're running out of time. Uh-oh. Yep, or you're going to be something else. But we're running out of time here. I want to save time for questions. So anyways, let me just go to the last slide. So these are some resources if you want more information on the stuff. I might do another talk on this if this isn't popular enough, but the idea is just if you want some more information on the architecture description, VTR docs are there, as well as example architectures. The global FPGA description, FPGA architecture principle and progression. I call this the Boutros and Betts survey paper. Very good paper if you want to learn more about this kind of stuff. And then local complex blocks, there's a whole paper by Jason Liu on this, as well as a tutorial in architecture modeling. So thank you guys so much for listening.